Hi, welcome back! In this lecture I'm going to focus on describing different coordinate systems in OpenGL and how to move from one to another using transformation matrices and GLM. In this lecture I want to make three key points. First, to transform our vertices from the local coordinates to the normalized device coordinates requires three major transformations: model transformation, view transformation, and finally projection transformation. Second, the final matrix combining model, view, and projection transformation is called MVP and is obtained as a matrix-matrix multiplication of the individual transformation matrices. Third, we can use GLM to form the model, view, and projection matrices and then pass them as math form uniforms to our vertex shader. In the last lecture we learned how we can use matrices to our advantage by transforming all vertices with transformation matrices. OpenGL expects all the vertices that we want to become visible to be normalized device coordinates. That is, the x, y, and z coordinates of each vertex should be between -1 and +1. Coordinates outside this range will not be visible. What we usually do is to specify the coordinates in a range we configure ourselves, and then in the vertex shader transform these coordinates to NDC. Transforming coordinates to NDC is usually accomplished in a step-by-step fashion, where we transform an object vertices to several coordinate systems. To transform the coordinates in one space to the next coordinate space, we will use three transformation matrices. The diagram on this slide displays the process and shows what each transformation does. Local coordinates are coordinates of your object relative to its logical origin. They are the coordinates your object begins in. The next step is to transform the local coordinates to the world space coordinates, which are coordinates in respect of a larger world. These coordinates are relative to a global origin of the world, together with many other objects also placed relative to the world's origin. Next, we transform the world coordinates to view space coordinates, in such a way that each coordinate is as seen from the camera or viewer's point of view. After the coordinates are in the view space, we want to project them to the clip coordinates. Clip coordinates are processed to the -1 to the +1 range. You probably got an idea why we use different transformation. The reason we are transforming our vertices into all these different spaces is that some operations make more sense or are easier to use in certain coordinate system. For example, when modifying our object, it makes most sense to do it in the local space. Calculating certain operation on the object with respect to the position of other objects makes most sense in world coordinates. If we want, we could define one transformation matrix that goes from a local space to the clip space, all in one go, but that leaves us with less flexibility. Local space is the coordinate space that is local to our object. All the models we have created so far all have 0, 0, 0 as their initial position. All the vertices of our model are therefore in local space. They are local to our object. The vertices of our triangle we have been using are specified as coordinates between -0.5 and +0.5, with 0.0 as its origin. These are local coordinates. If we would import all our objects directly in the application, they would probably all be somewhere stuck on each other around the world origin of 0, 0, 0. Instead, we want to define a position for each object relative to a position in a larger world. The coordinates in the world space are exactly what they sound like, the coordinates of all our vertices relative to a world. This is the coordinate space where we want our object transformed to, in such a way that we are all scattered around the place. The coordinates of our object are transformed from local to the world space. This is accomplished with the model matrix. The model matrix is a transformation matrix that translates, scales, and rotates our object to place it in the world at a location or orientation they belongs to. The view space is what people usually refer to as the camera of OpenGL. The view space is the result of transforming our world space coordinates to the coordinates that are in front of the user's view. The view space is the space as seen from the camera's point of view. This is usually accomplished with a combination of translation and rotation to rotate the scene so that certain items are transformed to the front of the camera. These combined transformations are generally stored inside the view matrix. In the next lecture, we will discuss how to create such a view matrix to simulate a camera. At the end of each vertex shader, OpenGL expects the coordinates to be within a specific range, and any coordinate that falls outside this range is clipped. Coordinates that are clipped are discarded, so the remaining coordinates will end up as fragments visible to our screen. To transform vertex coordinates from view to clip space, we define a so-called projection matrix that specifies a range of coordinates. The projection matrix transforms coordinates within this specified range to normalized device coordinates. All coordinates outside this range will not be mapped between -1 and +1, and therefore they will be clipped. This viewing box a projection matrix creates is called frustum, and each coordinate that ends up inside the frustum will end up on our screen. The projection matrix to transform view coordinates to clip coordinates can take two different forms with different frustum. We can either create an orthographic projection matrix or a perspective projection matrix. An orthographic projection matrix defines a cube-like frustum box. It defines the clipping space where each vertex outside this box is clipped. When creating an orthographic projection matrix, we specify the width, the height, and the length of the visible frustum. All the coordinates that ends up inside this frustum, after transforming them to the clip space with the orthographic projection, won't be clipped. To create an orthographic projection matrix, we make use of the GLM's built-in function glm_ortho. An orthographic projection produces unrealistic results, since the projection doesn't take perspective into account. We can mimic real-life perspective using a perspective projection matrix instead. The projection matrix maps a given frustum range to clip space, but also manipulates the W value of each vertex coordinate in such a way that further away vertex coordinate is from the viewer, the higher these W components become. Each component of the vertex coordinate is divided by its W component, giving smaller vertex coordinates the farther away a vertex is from the viewer. This is another reason why the W component is important, since it helps us with the perspective projection. A perspective projection matrix can be created in GLM using GLM perspective function. Finally, we can create the MVP transformation matrix. No, it's not the most valuable player matrix. It is a matrix that combines the three transformations we saw before: model, view, and projection transformation. A vertex coordinate is transformed to clip coordinates multiplying the individual matrices. Note that the order of matrix multiplication is reversed. Remember that we need to read matrix multiplication from the right to the left. The resulting vertex should then be assigned to the GL position in the vertex shader, and then OpenGL will automatically perform perspective division and clipping. We can now put everything together. We create and apply an MVP to our first triangle using the code available on Canvas called MVP_trans_first_triangle.cpp. We use GLM to form the model, view, and projection matrices on CPU. We move them to the vertex shader on the GPU using uniforms. Finally, we can make the matrix multiplication in the vertex shader on the GPU. Let's try to check the code, compile it, and run quickly. We can give a quick look at the source code. Let's look at the vertex shader source code. As you can see here, we define three matrices to represent the three transformations: the model, the view, and projection transformation. We have our input vector, vec4, including the vertex position, and then we multiply first by the model projection, the view transformation, and projection transformation. We define this transformation in the render loop of our OpenGL application. As you can see here, our model transformation is simply a rotation. The view transformation is simply a translation. And then we use a perspective projection. We compile it and run it. We are done with this lecture. In summary, in this lecture, I have emphasized three important points. First, to transform our vertices from local coordinates to the NDC requires three major transformations: model, view, and projection transformation. Second, the final matrix combining model, view, and projection transformation is called MVP and is obtained as a matrix multiplication. Third, we can use GLM to form the model, view, and projection matrices, and then pass them as Mat4 uniforms to our vertex shader. We are done with this lecture. In the next lecture, we are going to look at cameras in OpenGL and how to use GLM to implement cameras. Talk to you soon!